Let's explore how to work with cross-sections in the Grasshopper To AXISVM add-on. Our new component called Deconstruct Cross-Section is introduced in this video, as well as an improvement, the selection of multiple cross-sections from the AXISVM cross-section library with one component. First, I create a parametric cross-section. Click on the arrow to open the list of cross-section shapes. I select the rounded rectangle shape now. The input parameter list of the component is automatically adjusted to the selection. Clicking on the Show Image or Hide Image button, user may display or hide the sketch of the cross-section with the signs of the cross-section parameters. I connect the panels to the input parameters. The input values must be in meters. As soon as I fill all necessary inputs, the parametric cross-section is defined. I connect the output of the parametric cross-section component to the brand new component called Deconstruct Cross-Section, and the output parameter names are immediately adjusted to the parameter names of the input cross-section, and the numerical values are available on the output. As second, I use the cross-section from text component. I connect the name of the cross-section I want to find in the AXISVM cross-section library. The component returns the first occurrence of this cross-section name. If I need another cross-section table, I may feed the CS table input to configure the result. If I connect it to the Deconstruct cross-section component, there's a warning message telling that the output count is less than required for an I-shape cross-section. However, the visible outputs are filled with the cross-section parameter values. I right-click on the middle of the component to open the pop-up menu and use the Match Output feature to adjust the output count and make all parameter values available. Third option is to browse the AXISVM cross-section library with the improved AXISVM cross-section component that allows to select multiple cross-sections. Double-click the left side of the component to open a form. On the left side, user can select from the shapes and tables. The list box on the right side is filled with all cross-sections of the selected table. User may select one or more cross-sections from the list using the Shift and Control buttons of the keyboard. I select now 2 strips and click OK to confirm. Since I deconstruct more than one cross-sections now, I graphed the input parameter to group the values on the output. These rectangular cross-sections have only 3 parameters. To remove the unnecessary 4th output parameter, I use the Match Output feature of the pop-up menu. I keep the first selected cross-section and create a custom rectangular cross-section based on that. For this purpose, I take the parametric cross-section component, set the shape to rectangular, and set an expression for input parameter h that is going to duplicate the received number. Then I feed the inputs with the dimensions of the cross-section from the library, give it a name, and set the process to rolled. Last, I would like to mention that the cross-sections created from thick polygons cannot be deconstructed since they do not contain information about any cross-section parameters. Thank you for watching. In this video, the usage of the Remastered AXISVM analysis control component is introduced. The Grasshopper script contains analysis settings for vibration, linear static, buckling, and nonlinear static analysis. They are going to be the input data for the analysis control component. They are represented with the relay components here. Let's start the vibration analysis by connecting the analysis settings and setting the start input to true. The calculation process is speeded up in the video. When the calculation is finished, the vibration result case is displayed on the appropriate output. We see that it is linear vibration, it is the first and only result case, calculated for a load combination, and contains 20 mode shapes. Connecting the linear static relay, the analysis starts. The model is automatically saved before and after the calculation. This is why a valid file path is a mandatory input. Now we can compare the list of result cases with AXISVM. The load cases, load combinations, envelope and critical result cases are all part of the list. If we would like to run further analysis, we must zoom the analysis control component and add extra input parameters by clicking on a black plus sign. The output count is automatically adjusted. If we want to connect or change more than one analysis setting at once, we must set the Boolean toggle to false. Then we are free to, for example, connect two more analysis settings, and when we start the process, all modifications are considered. The vibration and linear static analysis is not repeated. The component simply reloads the detected valid result cases. The finite element calculations are executed according to the input order of the analysis control component, from top to bottom. AXFEA1 input is solved first, then AXFEA2, 3, and so on. Only the AXFEA1 is mandatory input, that's why it is bold. The others are optional. User may even leave some gaps, for example, connects nothing to AXFEA2, but connects something to AXFEA3. The nonlinear static analysis is also finished, and the result case list can be compared with AXISVM. The user may reduce the input count by zooming the analysis control and clicking on any of the white minus signs. Let's change the order of the analysis settings. Take the buckling first and linear static FEA second. The result case lists are found. Now let's tell that we want to have 10 buckling mode shapes instead of 8. In this case, the buckling analysis is restarted. Result cases of the linear static FEA are simply reloaded. If the dimensions or items of the model are changed, the analysis control can't find any available valid result. Therefore, all finite element calculations are repeated automatically after the data transfer. In this video, I introduce how to work with result cases, how to configure them to have the appropriate input for result display, result import, or cross-section optimization in the Grasshopper To AXISVM add-on. For this steel frame structure, the result case lists of the linear static analysis and the buckling analysis are available in Grasshopper on the output side of the AXISVM analysis control component. On the component palette, there is a new subcategory called Results that includes the Configure Result Case component. This can be used, for example, to choose between min and max envelopes and select the mode shape of interest. Let's take the result case list of the linear static FEA. The list item component is connected to the AXResultCase1 output of the analysis control component. I select now the load combination called ULS from the list and connect this result case to the configure result case component. The same value appears on the output. For display purposes, it may be important to see this result case on the Steel or Timber Design tab in AXISVM. To consider a linear or nonlinear static result case as Steel or Timber Design result case, I connect a valid design member to the bottommost input of the component. Thus, the result case of the output is turned to be a Steel or Timber Design result case depending on the type of the design member. Notice that the result case on the input side is not affected. See another example. Let me select the critical combination from the linear static result case list. Thus, the input parameter min-max type and crit.com type became relevant. They are not gray anymore. Opening the pop-up menu of the component with a right-click and create a list of min-max type and critical combination types displays and connects the related value lists. If I change the settings, the output result case is adjusted immediately. Now I take the result case list of the buckling analysis. In this case, the second input parameter called level shape time ID is relevant. The mode shape, load level, or time step number 1 is selected by default. I may set any other value between 1 and the available maximum. In this case, we have 12 mode shapes, as you can see in the description of the result case. Finally, I go back to the first example to show that multiple result cases may also be configured at once. Both result cases on the output are considered as Steel Design result cases, and for example, if I change the min-max type, the envelope result case is adjusted. The load combination is not modified, of course. In this video, the usage of the new AXISVM result display settings component is introduced. This AXISVM model contains the results of the linear static analysis and a buckling analysis performed on a parametric steel frame structure. The result case list is available on the output of the analysis control component. Now I go to the result display settings component. The AX result case input is currently empty, therefore only the view and model display inputs are considered. To apply the display settings, the start input must be true. Beside the Boolean toggle, I apply a gateEnd component here, and the input A gets its value from the done output of the analysis control component to ensure that these components communicate with AXISVM after each other and not parallel to avoid issues in data transfer. If I set the toggle to true, the selected view and model display type becomes visible in AXISVM. Below these value lists, you can see the result type and result component value lists, which work strictly together. I show this after connecting a buckling result case. Now I open the result type value list. If I change the result type to buckling displacement, the value list of the result component is renamed from line force to buckling displacement, and the value list is filled with the appropriate result components. The selected result component is displayed in AXISVM, and I can change with a Boolean input whether to display deformed shape or not. Let me change the result case to a load combination on the Steel Design tab. I open the result types again. You can see that all result types are included. They are organized similar to the AXISVM logic. I mean, displacements, strains, forces, and stresses follow each other for line elements. The truss, beam, and rib results are not separated. And then for surfaces, other items like support, spring, gap, or link internal forces come afterwards. Then buckling, vibration, and design member results. User must take care to select between steel and timber results, and for steel, there's a separate option for the Swiss standard. This example is calculated according to Eurocode standard, therefore I select the other option. I set the result component to MCR and the result display mode to field diagram. Then I change to line shear force to demonstrate the influence of result case configuration. I go to the source of our result case input. Currently, the results are displayed on the Steel Design tab. As you may saw in our other video, this is achieved with the Configure Result Case component that has a linear static result case as main input and a Steel Design member as the bottommost input to tell that we want to work on the Steel Design tab. Disconnecting the design member means that the linear static result case remains as it is, and the results are displayed on the static tab. Reconnecting the design member, we go again to the Steel Design tab. Now I change the input of the result display settings component to a linear static critical combination result case and show you its source. The selected min-max type is displayed in AXISVM. And with a slider, I may choose another result case from the list, for example, an envelope. As a third example, I go back to the buckling result case. I align the settings and show the source of the result case. Here, with a number slider, I change the selected mode shape to any value between 1 and 12 in this example. To show the remaining features of the result display settings component, I go back to the Steel Design tab and select the nodal vertical displacements to be displayed. The right value to input of the result display settings component is currently set to false. This means that no labels are displayed in AXISVM. Setting the toggle to true means that the minimum and maximum values are displayed at all available locations, nodes and lines in this case. But instead of simple toggle, I may use a new component to fine-tune these settings. From the results subcategory, I take the right values to component. All its inputs are set to true by default. Let's hide first the nodal results. Then show all values, not only the minimum and maximums. Then go back to min-max, but show results at nodes instead of lines. So simple. I change to an envelope result case now and open the AXISVM display parameters to show which parameters are driven by the autoscale and displayed envelope inputs of the result display settings component. I would like to introduce the usage of the X color legend input as well. If no input is connected, the automatic settings are applied in AXISVM. As input, a new item of the add-on, the color legend settings component, can be used. I'd like to change now the level count of the color legend to 10 using the first input parameter. Then I show how to influence the gradient of colors, switch between reverse and normal gradient with a Boolean input. And there is an option to separate the positive and negative values with a 3-level legend. If this option is true, the custom level count is irrelevant and not considered. Okay, now going back to the legend with 10 levels and creating the legend type value list from the pop-up menu. We can choose from the legend types similar to the Values tab of the AXISVM color legend setup. I may define custom levels, feeding the component with a list of ascending numerical values. I take care to define the values in meters and disconnect the unnecessary level count input. It is important that the values must be in ascending order, but they are not required to be equidistant. The level intervals may vary. There is still one input parameter to be mentioned, the duration, which is practically a delay in seconds. This means that the done output of this component is changed to true with the given delay after the display settings have been applied. Thus, user may keep the results on the screen, for example, between two finite element analysis. As a closure, I'd like to mention that if the user selects an invalid or not available display setting combination, error message is quite rarely returned on the output of this component. AXISVM uses rather its available automatic or default display settings in such cases. Let me show the usage of the AXISVM getResults component that is located in the Results subcategory. The most important input parameter is the result type. The following types are available now: nodal displacement, line and member displacement, line and member internal force, nodal support and line support reaction force, line and member stress. Nodal displacement covers the vibration and buckling mode shapes as well. The component is able to handle one single result type at once. For envelope and critical cases, user must select one or more result components as a basis of the envelope or critical results. The contents of the result component value list are always adjusted to the selected result type. I show some examples. If I define what kind of results do I need and which result components are of interest for envelope and critical result cases, I still need to feed the aux result case input to tell the component which result cases should it import results from. I must also define the locations I want to check, nodes in this case, and there are different ways to do this using the item ID input. First, I use the list of the node IDs of the upper corners, 8, 10, 18, 16, and set the start input to true. I work with an envelope result case, and I request it for results for both min and max envelope. The results are imported for min and max envelope separately. Therefore, I see that my input result case is split into two result cases on the X result case output. The bottommost output, called xResult, contains the imported results. In the panel, only the text description of the results is available. In order to be able to use the result values directly, users should connect an AXISVM deconstruct results component. The usage of that component is not part of the current topic. I make now a quick check of the results at node 8, and 10. Nodal displacements are, of course, always provided in the global coordinate system. The values are the same, just the dimensions are different. In Grasshopper, the displacement is in meter, and in AXISVM, it's currently in millimeter. I have a panel here. It contains -1. I connect this to the item ID input, telling the component that I need the nodal displacement of all nodes. I show the outcome, node 1, 2, 3, and it goes till the last node, it's node 112. This feature, to get the results for all items of the given type, is available for the highlighted result types at the moment. So if I choose the member displacement, I still get a warning that this is not yet possible. However, I can, of course, get member displacements for specific members. Here I have 3 AXISVM line parameters, and with Ctrl and left arrow, I go to the source of them. On the sketches, you can see that I have a group of the vertical beams, a group of the horizontal beams, and a group of the truss members. I type this information into relays here. In AXISVM, I changed to the member IDs instead of node IDs. A line and member displacement is available only for beams and ribs. Therefore, I import the results for the vertical beams. You can see that the results are listed section by section. In this model, every beam of the structural member is meshed with 4 lines, or in other words, with 4 finite elements. And we have the default 11 sections per line. If I select the line displacement, the results are listed by lines and not by structural members. To display the line indices in AXISVM, I should check the display options, numbering, labels and tables by finite elements option. I show an example for line number 9, where the section position goes from 0 to 0.875, that is the length of the line element. For both line and member displacement, the user can set with the local CSys Boolean input whether to get the global or the local displacements. Default setting is local. I display the support IDs in AXISVM and change to nodal support reaction force in Grasshopper. I get a warning message telling that I need to check the data connected to the item ID input, because it is not nodal support, but something else, and that's right. So I connect the AXISVM nodal support parameter instead. This contains all the 6 nodal supports of the model. Let me align the settings in AXISVM and double check some values. If I would like to consider the envelopes for more than one result component, I may connect more than one value list. Or I change the value list type to checklist and select some result components there. As I increase the number of result components, I have more and more result cases on the output side, of course. Min and max for each result component. The result list is organized with the same logic. Look at the paths. I change to the member stress result type, and the independent stress point Boolean input becomes active. Just a very short explanation about this feature. The default value is false, thus the various stress calculation points will have the value corresponding to the queried extreme components combination. If this input parameter is set to true, the various stress calculation points will have the respective extreme. To demonstrate that user may import results for more than one result case at once, I define the two load cases and one load combination of the model as input, and compare some values with AXISVM, knowing that in Grasshopper I see kilonewton per square meter. Last but not least, I import the stress results of the truss members. You maybe realized that in AXISVM, both the truss and beam indices start from 1. However, in Grasshopper, the truss and beam member indices are not separated. In this example, we have 16 beam members, and the beam indices start from 1. Therefore, the truss indices start from 17, and this is mentioned in the text description of the results. Look that I can get the same stress results connecting the ID number 17. If I import some results from AXISVM to Grasshopper, the received information is always organized into a data tree. Now I'm going to explain the logic behind these data trees and show some examples how to handle the results in Grasshopper. I begin with the system used for the result cases. This is common for each imported result type. If my result case input is a simple load case, the data tree at the X result case output is represented by a single straight line in the param viewer. Path 000 is assigned to it. The original result case list consists of 9 items. It comes from a linear static analysis of a steel frame structure. I add the index of the critical case to my selection. Thus, I have 2 branches in the param viewer. The load case is still on path 000, and the critical case is on path 100. Let me lock the solver for a second and connect 2 more result components. Then remove the lock. And you can see that the second index of the path is increasing as we go over the different result components, and the visualization shows the 3 separate branches as well. If I change the min-max type input from min to min-max, the getResults component automatically splits this into min and max result case for each result component. Therefore, the last index of the path is changed to 0, 1, 0, 1, and so on to distinguish between these cases. Path indices always start from 0 on the output of this component, and the order of the result cases is determined based on the order on the input side. The param viewer shows that there are two sub-branches at each result component. Okay, quick summary. So the path of the output result cases contains always three indices. First one stands for the result case, the second for the result component, and the third for the min-max type. Inside the encircled region, the data tree is always built with this logic. This is completely common for all available result types. The item IDs and the result values are going to be added outside this circle. To provide more details about the data trees of the imported results, I take first the result type with the most simple data structure, the nodal displacements. First, I connect a panel to show the text description, and you can see that I have 3 result cases and 1 node. Then I go to the results subcategory and take the AXISVM deconstruct results component to get access directly to the result values. This component accepts one result type at once. If I connect the X result output to it, the output parameter names and descriptions are automatically adjusted, and the result type name is displayed in the message balloon at the bottom of the component. I show the contents of some output parameters. In the panels, you can see the result cases, the node ID I currently work with, and the displacement values in X and Y direction at node number 8 as data trees. If I merge the output values except of the output called header, I'm going to have an overview of the complete data tree. In this case, the paths with 3 indices represent the 3 result cases. The paths with 4 indices represent the node ID lists in each result case, and the paths with 5 indices represent each result component for each result case. We have 8 result components for nodal displacement, therefore we have 8 sub-branches here. I split this data tree and focus on the results belong to the first result case only. I show the contents in a panel, and you see that we have one single value in each branch. Then I lock the solver for a second and add 2 more nodes to my list. Look at the param viewer. Nothing has changed there. The reason of this is that the node IDs are stored in a common branch as data list, and the result components are stored the same way. For example, the displacement in X direction is stored in a list for node number 8, 9, 10 in this order. To make it more clear, you see the encircled region that contains the information about the result cases. The next level contains the node IDs, and the following 8 sub-branches contain the result components. Very similar data structure is used for the nodal support reaction forces. The next example shows the data structure of the structural member internal forces. This data tree is set up for 2 result cases and 8 truss members, and we have 7 available result components on the output side. Let me show the AXISVM model. I talk about these 8 diagonal truss members of the structure. This data tree is a bit more complex. I have separate branches for each truss member. The truss member is represented with one single line and one single section. Therefore, the data tree continues with straight lines. Then at the end, it is broken into 7 sub-branches for the result components. Now I change the input and request results for 2 beam members. These beam structural members are split into 8 finite elements during meshing. This is why I have 8 sub-branches. These sub-branches contain the section positions in the local coordinate system of the member as data lists. Similar to what we saw at the nodal displacement, that we have more values in a common branch. For the section lists of each finite element, we have the already mentioned 7 sub-branches for the result components. Similar data structure is used for line and member displacement, line internal force, and line support reaction force as well. The last representative example shows the structural member stresses for one single result case and for 8 truss members. Since the truss member is represented by one finite element and one section, there's again a straight line in the param viewer that leads to the 15 sub-branches of the result components. If I change the input to 2 beam structural members, I see that both members are split into 8 finite elements in this example, and each finite element has 11 sections now. Compared to the data tree of the member internal forces, it's new that each section has also its own sub-branch, and these are broken into further 15 sub-branches representing the result components. This is required to be able to store the results at each stress calculation points of the sections. I'm going to make further clarification about this later on in this video, but now I rather want to explain that the lines expression is in brackets on the param viewer because that intermediate path is not really a part of the data tree. You can see that I don't have any branch path with 5 indices, but the 5th index of the section paths is growing from 0 to 7 to group the sections according to the finite element mesh. Last but not least, I mentioned that similar data structure is used, of course, for line stresses as well. Okay, I finished the introduction of the data structure itself, and now I show some practical examples how to work with the data. I begin this part again with the nodal displacements. I have 2 result cases and 4 nodes in this example. I haven't talked about the very first output parameter of the deconstruct results component yet. This is called header because it contains the list of all other output parameter names, thus it may be used as a table header. The second output is always the result case, followed by the item IDs and sections if relevant. After these, the result components come one after each other. I connect every single output to a panel to show all the contents of the component in an organized way. The dimension of these output values may differ from the dimensions you use in AXISVM. The dimension of the result values may be found in the description of the X result output and in the description of each output of the deconstruct results component. The displacements on the screen are in meters and the rotations are in radians anyway. You may have recognized that the nickname of each panel had been adjusted to the output parameter name as I connected them. This is the default behavior, and if you right-click on the component and deselect the Adjust Panel Nicknames option of the pop-up menu, every nickname is changed to panel. This feature affects only those panels that are directly connected to the output parameters and no intermediate components are inserted. I activate this feature again for better understanding. And I mention here that the dimension of the result component is not displayed in the panel nickname because we wanted to avoid to let there any misleading text if user may divide or multiply the result values in the meantime. I show how to copy the data manually into an Excel table. I use the copy data only feature of the panels and paste the data somewhere. For the first paste, somehow I have limited options to format the data. Therefore, I use the Ctrl+C combination to copy again and paste the data into cell A now. Then I choose the transposing from the special paste options and then remove the unnecessary text. You may realize that the result case panel contains only 2 lines. But I have 4 nodes per result case, and if I want to have a correct table, I need to have each result case name 4 times. Therefore, I take the length of the node ID list and tell the result case output to be repeated 4 times. I copy the data, and to remove the extra lines, I use a special pasting process again. Here we are. The paste of the numerical values goes simply. Just the number formatting must be adjusted by the user. With this method, we get a, so to say, offline table that is not automatically updated with any changes in the data. After the nodal displacements, I talk about the structural member internal forces. The panels on the right side are connected with invisible wires to the appropriate outputs of the deconstruct results component. You can see in the panels that for truss members we have a very simple situation because one section and one result value belongs to each member. I mean, the data count is the same in these branches and no adjustment is required if you want to make a table from the data. In case of beam structural members, it's obvious that we see more sections than member IDs. To calculate how many sections belong to each member, first, I merge the 3 relevant outputs of the deconstruct results component. The outermost branches contain the section lists grouped according to the finite elements of the structural member. As I mentioned earlier, in this example, each structural member is divided into 8 finite element lines during meshing, and each line consists of 11 sections. To automatize the calculation, I use the path mapper component, where you can see that the input data of the path mapper, the section output parameter, has passes with 5 indices, A, B, C, D, E. I want to know how many sections belong to one structural member. Therefore, I remove letter E from the right side. This means that I merge all the section subbranches to the level of their structural member. You see A, B, C, D. You can check also here that structural member paths have 4 indices really. The tree statistics show that we have the required 4 branches and we have 88 sections per structural member. We know that this is correct since the 8 finite elements per member multiplied by 11 sections is exactly 88. So I take the member IDs, tell them to be repeated 88 times inside the branches. It is important that I have a data tree on the first input and I have a data list on the second input called length, and I must graft the length input to get really what I want. Now let me talk about the most complex data structure as well. If I connect the structural member stress results to the AXISVM deconstruct results component, the output parameters are adjusted, but I get a warning message. This tells me that the output count is less than the available result component count. I can solve this using the Match Outputs feature from the component pop-up menu. This expands the component and displays all available outputs. Below the section output, you can find the minimum, maximum, and mean stress components of the given section. Then, the SCP-ID output contains the list of stress calculation point IDs that belong to the given section. And then the detailed result components are available in each stress calculation point of the section. Let me represent this by connecting the member ID, the section, the SMIN, the SCP ID, and the SSCP outputs to separate panels. Currently, we see the results for a truss member, that's why it's very clear and simple. One section and one stress calculation point per section belongs to each member. If I change the input to beam structural members, the data contents of the panels are quite different. Here you can see that, for example, 9 stress calculation points belong to the section number 0. I have already shown how to repeat data, therefore now I would like to do something else. Let me say that I'm looking for the results in the stress calculation point number 1 of each section. So, using the index 0, referring to the very first item of a list, I take the first item in each branch of the SCP-ID output and the first item of each branch of the SSCP output, and I display the outcome in the last 2 panels to get an overview. As a closure, I gathered some useful components to work with the introduced data structure. The param viewer from the params tab utils subcategory often helps to understand the relation of branches, and the other 6 components from the sets tab help to modify the data count or filter the results. From other add-ons, you may try to use the Heteroptera min-max component when searching for an extreme value, and the Write to Excel component from TT Toolbox to export some data into Excel sheets. Thank you for watching. I'm going to show now how to perform cross-section optimization in AXISVM with the brand new component group of the Grasshopper To AXISVM add-on. The components can handle steel as well as timber design members. In this example, I work with a parametric steel frame structure, but the usage of components would be exactly the same for timber design members as well. You can see that I have steel design members on the vertical and horizontal beams, and the structure contains some members with unacceptably high utilization values. Our new components can be found under the Optimization subcategory of the AXISVM tab. There are 5 components in total, and I'm going to introduce them one by one and show how they must be connected with each other. I focus first on the general optimization settings. This component covers the encircled part of the cross-section optimization form. These settings are common for parametric optimization and for optimization from predefined shapes. User may select the objective of optimization using the value list, set the maximum allowed utilization, and set the Boolean inputs of the optimization checks to tell which of them need to be considered and which not. All these inputs are set to true. This means they are going to be considered by default. The strengths checkbox is not represented on the Grasshopper component. It is always considered as true input in the background because it is essential for the optimization. Thus, it is permanently selected even in AXISVM. I go on to the settings of a parametric optimization group that is going to contain the vertical design members. The top 3 inputs are the name of the optimization group, the design members to be added to the group, and the general optimization settings that I have just introduced. The cross-section parameter on the left side contains the cross-section of the design members, and with the new deconstruct cross-section component, its cross-section parameters are available and can be used to set up the cross-section parameter limits of the parametric optimization group easily. These values are always in meters in Grasshopper. To define the parameter limits, the most simple way is to connect a numeric value, for example, taking the appropriate output of the deconstruct cross-section component. I do this for the height and width. With this approach, the parameter limits are calculated according to the default rules of AXISVM. For the 0.27 meter height, the lower limit is the half of this value, and the upper limit is equal to 2 times this value. The delta step size is set to 0.05 meter in this case. Same logic is applied for the width. If I would like to fix any of the cross-section parameters during the cross-section optimization, the easiest way is to connect a true value as input that sets the given parameter to fix immediately. And I show a third option. I would use this if I would need completely custom limits. In this case, I would take the AXISVM optimization parameter limits component and set each value as I wish. It is sufficient to fill those inputs that are relevant for the current cross-section shape. The 3 bottommost input parameters tell AXISVM whether I would like to set a custom limit for the iterations and how many % of the most utilized beams should be considered during optimization. The input parameter called beams % accepts round values that may be divided by 10. To ensure this, I took a number slider going from 1 to 10, and I set an expression x multiplied by 10 to provide valid input all the time. To really understand the meaning of these inputs, I displayed a screenshot of the AXISVM user interface again, and I mentioned that the cross-section optimization in AXISVM may happen 2 ways currently. In this case, in case of PSO optimization, the form looks like this, and you can see easily how to set custom iteration count and how to change the considered beam amount. However, in case of simple optimization, these settings are simply not relevant, not even available. AXISVM decides which optimization method is going to be used for the groups. So it works to define these input parameters in Grasshopper, knowing that they are used only if PSO optimization is performed. Let me fix the flange thickness parameter as well to speed up the upcoming optimization process, and then go ahead to the configuration of optimization groups for optimization based on predefined shapes. I'm going to set up a group for the horizontal steel design members. The first 3 inputs of the component are the same as we saw earlier at the parametric group: name, design members, and the general settings. The cross-section of the design members is IPE 400. I select some cross-section candidates from the same cross-section table. This is very quick since the AXISVM cross-section component is improved and allows multiple selection now. I may take cross-sections that are already part of the model as well. I connect the list to the optimization settings component. The component still needs lower and upper limits for cross-section height and width. I use the deconstruct cross-section component, and first I connect the height value to hmin and hmax, and the width to bmin and bmax, then set expressions to each parameter. The lower limits are calculated as half of the h or b value. The upper limits are equal to 2 times the h or b value. I could also do that I connect my cross-section candidates into the deconstruct cross-section component, search for extreme values of the height and width, and connect those extremes to the input parameters. If this is done, I can check the limits, for example, in the text description of the optimization settings. We arrived now to the AXISVM cross-section optimization component, where every setting I explained can be combined together and the optimization process can be started. This component is able to run optimization for either steel or timber design members. So it works for both, but they can't be combined within one optimization. The first input is AXUP, because this component communicates with AXISVM. The second input gathers the list of the optimization group settings, both parametric group settings and settings with predefined shapes can be connected, as many as you want. The only restriction is that one specific design member can be part of one single optimization group only. If it appears in more group settings, it is removed from the earlier groups. Error message is, of course, displayed about this information, and the design member is considered in its last group only. In my list, I have the two settings introduced earlier. The first one is the parametric group setting, and the second is the group with predefined shapes. I chose an envelope and critical case for this demonstration, and I show you in AXISVM that the envelope result case results in higher utilization. Before I start the optimization with the Boolean input, I move the toggle below the panels because I would like to show also the information that appeared during the optimization process. If I start, the parametric group is immediately created, then the candidates of the other group are added, and when the groups are created, the optimization starts for the first result case and first group, which are the envelope case and the parametric group in this case. The progress is displayed continuously, and in the end, the finished or finished with errors message appears. In the second case, you would see some error messages in the second panel, of course. If every result case and group are checked, the done output is set to true, so the process is completed. To have the optimization results, there is no need to use any extra component. The X results output contains the available data for each result case and optimization group. The first index of the branch path stands for the result case. In this example, 0 is for the envelope and 1 is for the critical case. The second index belongs always to the optimization groups. In this case, 0 is for the parametric group, 1 is for the group with predefined shapes. Before going into more details about the results, I still show that the optimal cross-section output contains the cross-section parameters for the group with predefined shapes. If I display the contents, you can see that the optimization of the envelope result case shows necessity for a bigger cross-section to compensate the higher utilizations as expected. Then I changed the view to talk more about the results, and I focus on an Explode3 component that is connected to the XResults output and provides the 4 branches on separate outputs. The parametric optimization results of the vertical design members are collected in the panel on the left, and the optimization results for the horizontal design members based on predefined shapes are collected in the panel on the right. Beside the sketches, the data of the original member cross-sections are displayed. The optimization result descriptions always contain the group name, the optimization type, and the result case in the header. Then the utilization and cross-section data. I take the new AXISVM deconstruct results component to access the results directly and connect the branch 00 and 01 to one and the other component. You can see that the output parameter list is automatically adjusted, and at the bottom of the components we see that cross-section optimization results are deconstructed. The suffix par is for parametric groups, and the suffix ps is for groups with predefined shapes. The unnecessary output parameter at the bottom may be removed by right-click on the component and using the Match Outputs feature from the pop-up menu. The header output contains the names of the other input parameters, thus it may be used as a table header. Then the result case information, the optimization group, and its type is available. The details of the optimal cross-section, then the utilization values, and the change in the mass is available. The output parameter names are the same for the group with predefined shapes as well, but here we may get not only one value for one input, but a list of results, similar to AXISVM. If I open the cross-section optimization in AXISVM, you can see that the groups and their settings are stored, but the results not. I start the optimization process, first for the critical min-max. This is slightly speeded up in the video. You can see that these results match the values that I have in the bottom of the big panels. The only difference is that AXISVM assigns a cross-section name to the outcome of the parametric optimization. In Grasshopper, the cross-section name is created considering the cross-section parameter values. Then I run the optimization for the same envelope case I used in Grasshopper. And if I click on the arrow beside the cross-section, then I see the same 2 cross-sections for the group with the predefined shapes as I saw in Grasshopper. Thank you for watching.